On July 1st, 1959, the first day of this report period, responsibility for technical direction and funding of the Centaur program was transferred from the Advanced Research Projects Agency to the National Aeronautics and Space Administration. All other management responsibilities remained the same. Mr. Kraft Araki, director of the Centaur program at Convair Astronautics, will introduce you to this second motion picture progress report on Centaur.
During the last half year, in 1959, the Centaur project development work advanced from the drawing board to the fabrication of test vehicles and to evaluation testing. A large amount of this work was done by our associate contractor and our subcontractors. Consequently, a considerable portion of this film will be devoted to reporting their activities. As far as the development work at Convair Astronautics is concerned, the Centaur project engineer, Mr. Dean Davis, will report about it.
For the past 6 months, our efforts have been concentrated in proving design concepts, evaluating parts and components, and preparing the tooling for the first flight vehicles. In our computer laboratories, Centaur has undergone hundreds of simulated missions encountering every conceivable flight condition. On the analog computer alone, more than 3,000 hours were used during the report period to study launch conditions, fuel consumption, heating and pressurization, and the design of such units as the autopilot and guidance system. The computer studies have been extremely rewarding. We learned from studies such as this, for example, that, as originally planned, the fuel consumption of the attitude control engines would be so high that the propellant supply would be depleted before completion of the mission. The fuel consumption rate has been reduced, and the problem solved. The blinking lights represent the attitude control engines maneuvering the rear of the vehicle towards the sun during the coast phase. Information generated during computer studies is applied directly to the design and development of such units as the autopilot. This is a breadboard of the autopilot, undergoing a checkout test during the early months of this report period. Design, breadboard fabrication, and functional testing have now been completed on the autopilot programmer, servo amplifier and rate gyro group, and prototype construction has started on all 3 items. This tracking beacon antenna is undergoing a high-altitude chamber test, just one of the tests to which it and other Centaur components are subjected during the evaluation program. The antenna was tested at altitudes ranging from sea level to 50 miles, since it had been determined that this is the critical altitude range for the unit. The antenna completed all of the evaluation tests successfully. At the Convair plant in Fort Worth, Texas, tooling had been readied by the end of the report period to begin fabrication of Centaur's jettisonable nose fairing. Most of the fairing, which will protect the payload from aerodynamic heating during the Atlas booster phase of the mission, will be formed over this large tool. The Centaur nose caps are already in production. The caps are formed in a female mold from 11 layers of fiberglass and are then cured for approximately 4.5 hours in an oven at 350 degrees Fahrenheit. Here at Convair Astronautics, the second heavy-duty Centaur cruiser tank was completed during October. This tank is scheduled to be used by the Pratt & Whitney Aircraft Corporation in West Palm Beach, Florida, in a static test program. After initial fabrication, the tank was moved from the manufacturing area to a storage location where the insulation panels were installed. On flight vehicles, the insulation panels will be covered with black heat-resisting paint. The panels, constructed of closed-cell polyurethane foam sandwiched between thin layers of fiberglass, will be ejected from Centaur during the booster phase of the flight. The first cruiser tank, after completing a series of leak tests in the hydrostatic tower at Convair Astronautics, was shipped from the main plant in August to undergo liquid hydrogen tanking tests. Its destination was our Point Loma test site, located beside the ocean some 15 miles from our main facility. Here, all types of system evaluation programs with the exception of static engine tests, are conducted on missile and space vehicle systems. The Centaur test stand at Point Loma was completed on September 2nd, and the tank was installed just 2 days later. This test area was developed specifically for the Centaur program. The storage tank is capable of handling 20,000 gallons of liquid hydrogen. The liquid hydrogen is transferred to and from the cruiser tank through 165 feet of vacuum-jacketed transfer lines. The blockhouse, located some 250 feet from the stand, is fully instrumented. It is capable of receiving and recording over 100 channels of information during a test. Preparations for the first test started immediately after the tank was installed in the stand. The heat-resisting insulation panels were first mounted on the tank. 6 500-watt lamps were placed in special protective boxes and located inside the liquid hydrogen tank. The lights permit motion pictures to be taken of the interior of the tank during loading operations. 4 instrumentation motion picture cameras were located around the stand. This 16-millimeter camera was positioned on top of the tank. It viewed the inside of the tank through a prism and a double-plate plexiglass porthole. The first test was conducted on the evening of November 23, 1959, and lasted approximately 4 hours. Test objectives were the evaluation of the pressurization system and tanking procedures, and the study of chill-down, boil-off, and heat gain rates and condensation losses during the hold time. The tank was first purged with gaseous nitrogen and then gaseous hydrogen to remove potential oxidants. The liquid oxygen tank, located below the hydrogen tank, was pressurized with helium to 40 pounds per square inch. After a chill-down period to condition the transfer system and the tank to receive the minus 423 degrees Fahrenheit liquid hydrogen, the tanking operation started. The liquid hydrogen entered the 8,000-gallon tank at a rate of 900 gallons per minute. This black and white film was taken by the instrumentation camera on top of the tank. After the tank was filled, liquid hydrogen boil-off was measured, and then the tank was filled again. The boil-off rate was within 5% of the pre-test calculation. The test, which was completely successful, marked the first time that a thin-walled tank of this size has contained such quantities of liquid hydrogen. On December 22nd, a second evaluation and study tanking test was conducted. Again, the test was successful. All test objectives were attained.
Months before the successful tanking tests at Point Loma, a study of the characteristics of liquid hydrogen was conducted by Arthur D. Little Incorporated of Cambridge, Massachusetts. That study will be reviewed by Win Sawyer, director of the project.
Arthur D. Little Incorporated, under contract to the Air Research and Development Command, has been conducting a study of the hazards associated with the handling and storage of liquid hydrogen. Tests conducted under the program were made at our facilities at Otis Air Force Base on Cape Cod. During the first phase, we investigated hazards associated with major spills, pipeline breaks, venting, and condensation of solid air in liquid hydrogen. In early tests, we measured the blast potential of mixtures of gaseous hydrogen and oxygen. These mixtures were ignited while held within a 5-foot latex sphere. Detonation occurred only when the concentration of gaseous oxygen was 40% or more and when an explosive igniter was used. Here you see a test in which 32 gallons of liquid hydrogen was deliberately spilled and ignited at normal atmospheric conditions. Later experiments involved the spilling and ignition of quantities up to 5,000 gallons. Additional tests were made during which liquid hydrogen was ignited in the presence of solid air. These established that detonation occurs only when there is oxygen enrichment. These are representative of a wide variety of tests which have been made. An evaluation indicates that liquid hydrogen is safer to handle than had been previously considered and safer to handle than many other missile propellants. We are now running tests on liquid hydrogen combined with liquid oxygen. When the mixture is ignited, an accurate record of the blast is obtained. This information will be useful in establishing safety procedures and in the design of launch support equipment for hydrogen-propelled space vehicles.
Some of the launch support equipment was produced by HACL Johnston Incorporated of Columbus, Ohio. Founder and president of the company is Dr. HACL Johnston.
All three of the liquid hydrogen transfer line units for Centaur were completed by August 1, 1959, within 65 days after we received the contract. Because of our previous experience in producing similar hardware, we were able to fill the order rapidly. The Centaur ground support lines transfer liquid hydrogen with a minimum of leakage and heat loss. Our tests showed that the leakage rate for the lines is 10% less than the specifications require. To prevent heat from affecting the propellant, we constructed the stainless steel lines with double jackets. A 3-inch inner line is suspended inside a 5-inch outer jacket, and a nearly perfect vacuum is maintained in the space between the lines. To further reduce heat penetration, we wrap the inner liquid line with 3 layers of aluminum foil. This serves as a radiation shield. This specially designed low heat leak bayonet type union permits easy, rapid assembly or disassembly of the line unit. The lines are carefully inspected to ensure that they are leak-proof. A mass spectrometer leak detector using helium gas as a tracer element monitors for leaks. If traces of helium penetrate a seam, the spectrometer reacts and the location of the leak is pinpointed. X-rays are also taken of all welds to determine that they are free of cracks, gas pockets, and embedded dirt. Design concepts similar to those used with the transfer lines were employed to produce the liquid hydrogen storage vessel. The inner tank is suspended inside the outer shell by means of a low heat leak suspension system. We packed approximately 14,000 pounds of a powder insulator in the vacuum space between the tank walls to reflect radiation. The boil-off rate for the tank is below 0.9% of the total volume per day.
The Minneapolis Honeywell Regulator Company, near St. Petersburg, Florida, is developing Centaur's all-inertial guidance system. Project manager is Charles Durham.
The all-inertial guidance system for Centaur represents a new generation in guidance. But the heart of the system, its inertial platform, will function similar to this early model, which was developed for the Beaumark missile. As you know, the guidance system will pinpoint Centaur's location, velocity, and attitude during the powered flight by measuring its acceleration along 3 axes. 3 precision accelerometers mounted in a stabilized inner cluster, such as in this unit, will measure the acceleration. During flight, the inner cluster will maintain its angular orientation in space, as shown by this laboratory demonstration. 3 extremely sensitive miniature gyros will govern torque motors in the gimbal to make adjustments for the vehicle's angular motion. By knowing the vehicle's location and velocity, the guidance computer will make the necessary calculations and subsequent engine adjustments, including shut-on and restart, to guide Centaur on its assigned mission. The guidance system will also point the vehicle towards the sun during the coasting period and reposition it for each new powered phase. This gyro, undergoing an acceptance inspection, was manufactured at our facility in Minneapolis, Minnesota. It is placed in a small heater oven during the test. We began design studies and the actual manufacture of some components immediately after receiving the contract in July 1959. By December, we were well into final assembly of the first unit. The accelerometer, small as it is, plays a major role in the guidance system. A floated pendulum inside the unit, reacting to acceleration, emits digital signals. The signal pulses, representing increments of velocity, are counted and used directly by the computer in its operation. Most of the parts and sub-assemblies for the guidance system are manufactured at our inertial guidance center. Parts such as this intercluster casting are machined here. The circuitry, transistors, and tubes are assembled by our technician. This technician is checking out a wiring pattern on a mock-up of the inner cluster. Solid magnesium is used for the gimbal frame castings, which are custom machined to precision tolerances. Assembled to these castings are the torque motors, bearings, slip rings, and synchros which support and stabilize the inner cluster. 5 units, all relatively small because of transistors and miniaturized components, comprise the entire guidance system. They weigh less than 150 pounds and occupy less than 4 cubic feet of space. The computers for the Centaur guidance system are under development at the Airborne Engineering Department of Leaperscope Incorporated in Glendale, California. Henry Norris, chief engineer of the department, will report on the status of that program.
Although we are not scheduled to deliver our first computer until April of 1960, we have been bench and flight testing prototypes of the unit for 2 years now. The transistorized digital computer, which will direct guidance and staging sequences in Centaur, will be almost identical to this prototype undergoing a checkout test. This particular computer weighs about 30 pounds and occupies about 1/2 of a cubic foot of space. It is a general-purpose digital computer containing a magnetic memory drum with over 2,000 words of storage. The drum and other components for the Centaur computer have been tested up to 2,000 cycles and have passed the 6G vibration in all 3 axes. We began the preliminary engineering for the computer in May of this year. While establishing system tie-in and computing requirements, we started to custom-build parts for the computer design verification. The circuitry in the Centaur computer will use silicon transistors and diodes, similar to this circuit card from the prototype computer. The design development and design confirmation testing phase for the Centaur computer is closing, and the manufacturing phase is beginning.
In Dallas, Texas, the apparatus division of Texas Instruments Incorporated is producing the telemetry units for Centaur. Joe Smith, head of the Missile Department Instrumentation Section, will review the program.
Design concepts, which we proved on other missile telemetry programs, plus an emphasis on miniaturization, were used to develop a small, extremely rugged telemetry unit for Centaur. In design, the Centaur system is similar to this unit, which survives the impact of a Minuteman missile during a tether test. Although the unit was subjected to a force between 1,000 and 20,000 G, it operated normally after removal from the wreckage. The key to the size and weight saving of the Centaur unit is the miniaturization of components. This transistorized subcarrier oscillator, for example, is less than half the size of its vacuum tube counterpart. 13 subcarrier oscillators are used in the 18-channel FM-FM telemetry unit for Centaur 1. By using miniaturized components, we were able to develop a unit which occupies 1/2 a cubic foot of space and weighs only 20 pounds. This is 20 pounds lighter than required by the original specifications. As you can see in this 2 to 4 watt transmitter, silicon transistors are used wherever possible. 53 transistors and only 4 tubes are used in the entire Centaur 1 unit. Transistors are employed at lower frequencies and power levels to yield the most savings in weight, space, and power for the transmitter and for the entire unit. Ceramic tubes are brought in where power and frequencies increase. We received the contract for Centaur 1 telemetry in July 1959 and completed the first unit in November. After a final checkout of the initial system, we shipped it to Convair Astronautics on December the 2nd, 1959. Essentially, the Centaur units are high-fidelity telemetry. They are designed to operate continuously up to 500 hours without adjustment, transmitting flight data accurately and clearly from interplanetary space.
The Bell Aircraft Corporation, Niagara Falls, New York, is producing Centaur's attitude control thrust chambers. Technical director of the project is Art Gorbety.
Hydrogen peroxide thrust chambers were developed as a solution to the high-altitude, high-speed attitude control problems which were first encountered in the Bell X-1A in 1953. Bell Aircraft has since developed additional thrust chambers which have been provided for another high-altitude experimental aircraft and have currently under development thrust chambers for the manned space program. This is a 50-pound thrust unit mock-up which is to be used on the Centaur vehicles. 4 of these will be delivered for each vehicle. Each thrust unit consists of a conical nozzle thrust chamber containing a catalyst which initiates and maintains decomposition of hydrogen peroxide and a solenoid-operated feed valve. Thrust chambers used during the early phases of R&D testing are shown here. The test units have a simplified inlet configuration and are without the divergent part of the thrust nozzle. Chambers for 3 of the 4 levels of thrust for the Centaur vehicles are shown: 50 pound, 1.5 pound, and 3 pound. 2 types of catalyst beds are under evaluation and are also shown. One type consists of a series of cups containing the catalyst screen. The other catalyst consists of a flame-sprayed stack of catalyst screens. The components used in a hydrogen peroxide feed system must be carefully cleaned and in some cases chemically treated to reduce the decomposition rate of the hydrogen peroxide in contact with the material. The area shown here is utilized by the manufacturing department to clean and chemically treat components of deliverable systems. After cleaning or chemical treatment, the parts are immersed or filled with hydrogen peroxide to evaluate their compatibility with the monopropellant. Compatible components are carefully wrapped in plastic bags to prevent inadvertent contamination of the components during handling. In flight, hydrogen peroxide is contained in a bladder inside a pressurized sphere. Helium gas compresses the bladder, forcing the propellant into a perforated discharge tube and out of the tank to the thrust units. This type of an arrangement is unaffected by zero gravity. Test cells for evaluation and qualification of the thrust units are located at the main Bell plant. The test cells are utilized for 3 phases of testing. Development tests are conducted to determine the production configuration and to establish performance limits. Acceptance tests are conducted prior to delivery of production units to Convair. Design proof tests are performed concurrently with production delivery to verify performance under simulated flight conditions. This method of attitude control has been selected because of weight advantage, relative simplicity, ability to operate in the vacuum, and reliability of operation.
The Tesco Products Division of the Borg-Warner Corporation near Cleveland, Ohio, is producing the turbo booster pumps for Centaur. Tom Carpenter is the project manager.
The assignment for our turbine-powered pumps is to deliver hydrogen and oxygen in a subcooled liquid state to the turbo pumps of the Centaur's engine. Because of our previous experience with cryogenics, especially hydrogen, we were able to proceed rapidly through design, development, testing, and first deliveries. By June of 1959, approximately 90 days after we received our Centaur contract, we had finished all engineering drawings and had started to machine parts. Impellers, inducers, shafts, and other pump parts are custom-made in our experimental and prototype machine shop. Before final assembly, each pump part is ultrasonically cleaned in trichloroethylene. Electrostatically conditioned air, a constant cleaning program, and special work clothes for the technician keep this and the neighboring assembling area dust-free and hospital clean. After the part is inspected under an ultraviolet light to ensure that it's absolutely clean, it is mated to other parts to form the pump. High-purity aluminum and stainless steel are used in the pump. The bearings are lubricated by the propellants as they are pumped through the unit. Just 7 months after we started our Centaur program, the first pumps were undergoing preliminary tests at our test facility. This hydrogen pump, which weighs only 60 pounds when assembled with its turbine and gearbox, pumps 1,270 gallons per minute while maintaining a constant pressure of 18.5 pounds per square inch. Liquid nitrogen was used in early tests to check out the unit. It was first tested with hydrogen on October 19th. A hydraulic motor supplied the power during the early phases of the test program. This hydrogen pump design concept has been thoroughly proven. An earlier model pump, built for another project, operated some 260 hours without maintenance. This liquid oxygen pump test cell, which was constructed with company funds, was completed just before testing of the liquid oxygen pump was scheduled to begin. Development of the liquid oxygen pump has progressed on an even pace with the hydrogen unit. Water, which has properties similar to liquid oxygen, was used in preliminary tests. The pump's nominal flow rate is 397 gallons per minute to 65 pounds per square inch of pressure. Drive power was supplied by an electric motor. The turbines and gearboxes for both pumps were developed under our supervision by the Aircraft Accessory Turbine Department of the General Electric Company of West Lynn, Massachusetts. Progress at General Electric will be summarized by Warren Poole, project engineer.
The Centaur turbo drive units are an outgrowth of an existing power supply which was developed for the X-15 research aircraft. A similarity to the X-15 unit can readily be seen by comparing it with one of the Centaur power units, the AM-31, which drives the liquid oxygen boost pump. Operation of the unit can be illustrated by referring to this simplified schematic. 90% hydrogen peroxide is fed to a decomposition chamber. Upon contact with a silver screen catalyst, it decomposes instantly to steam and oxygen. The hot gas drives the turbine, which provides power through a gear train. Turbine speed is regulated by a feedback system to the control valve. The turbo drives are manufactured here at West Lynn and assembled in dust-free, environmentally controlled areas. The AM-31 weighs 39.5 pounds, delivers 37 horsepower, with an average specific fuel consumption of less than 11 pounds per horsepower hour. The AM-32 weighs 28.5 pounds, delivers 23 horsepower, with an average specific fuel consumption of less than 11.7 pounds per horsepower hour. The first unit for ground checkout was shipped to our Malta test facility, Boston Spa, New York, on October 7th, 1959. Here, the units are subjected to a complete evaluation of performance under simulated flight conditions. This is the AM-32 for the liquid hydrogen pump. Initial runs checked out overall performance, with every significant measurement recorded. Development and design proofing tests will be carried out concurrently with production and shipment of flight units. Our progress to date confirms our belief that turbine-driven boost pumps are an ideal answer to the space vehicle propellant supply problem.
The associate contractor on the program, Pratt & Whitney Aircraft Corporation, subjected experimental Centaur engines to intensive testing throughout the report period at its Research and Development Center near West Palm Beach, Florida. Directing development of the XLR-115 liquid hydrogen, liquid oxygen propulsion units is project engineer Dick Mulready.
The development program to date has confirmed that the basic design of the LR-115 engine is sound. The rated performance of 412 seconds impulse at 15,000 pounds vacuum thrust has been demonstrated, and firings have been made which exceed the durations required for Centaur missions. A unique regenerative turbopump cycle is employed in this engine, in which the heat rejected to the fuel in passing through the thrust chamber cooling tube provides the energy to drive the fuel and oxidizer pump. Because of the low initial temperature and the very high specific heat of hydrogen, the required turbine inlet temperature can be as low as 100 degrees Fahrenheit below zero. This permits a compact turbopump assembly, which is constructed for the most part from aluminum. An additional feature of this design is the hydrogen cooling of the gears and bearings, which eliminates the complexity of conventional lubrication systems. Thrust control is provided by a single valve, which adjusts turbine speed to maintain a preset chamber pressure. By the end of the report period, 4 complete experimental engines had been assembled for use in the test program. The thrust chamber is fabricated by furnace brazing the assembly of tubes, manifolds, and reinforcing structure in one operation. Transpiration cooling of the injector is provided by constructing the face of a permeable mesh material, which permits a small quantity of hydrogen to seep through. The complete flight engine will weigh less than 270 pounds. Major emphasis has been placed throughout the program on the development testing of engine components. To date, over 1,000 hours of component test time has been accumulated. Through this test effort, the practicability of using an unlubricated hydrogen-cooled turbopump assembly was proved. Some 70 different bearing configurations were subjected to more than 400 hours of development testing before the bearings for the turbopump assembly were selected. A new vertical test stand, designated E5, was completed in December, bringing to 5 the number of stands available for the Centaur engine test program. The new stand will be used to test 2 engines in conjunction with the Centaur tanks and propellant supply system. Space starting and running of the LR-115 engine is simulated on the test stand. The low pressure for starting is provided by a 2-stage steam ejector system, and running simulation is maintained by a supersonic exhaust diffuser. The first test of a complete experimental engine was conducted on July 25th, 1959. During the test program to date, the LR-115 engine has demonstrated its self-starting capability, stable operation with flight control, better than rated performance, simulated altitude starting and running, a sustained engine run of 335 seconds, 4 consecutive firings on one engine, 8 consecutive firings on one chamber, chamber firings to 18,000 pounds of thrust, and successive firings on a single engine totaling over 7.5 minutes.
By December 31st, 1959, Pratt & Whitney had conducted 67 Centaur engine and thrust chamber firings, accumulating a total operating time of 2,322 seconds. Engine firings alone accounted for 1,781 seconds of the total time. At the Atlantic Missile Range, Cape Canaveral, Florida, construction was well underway at the end of the report period on the launching complex for space vehicles. Construction of the complex, which has been designated Pad 36, started with the launch control blockhouse. Pad 36 is scheduled for completion in November 1960.
As you have just seen, The development of Project Centaur is progressing on schedule. The tempo of development will increase in the months ahead. At Conway Astronautics, we have completed tooling, and we will soon begin fabrication of the first flight vehicles. The first engines, turbo booster pumps, and electronic components will be delivered for final testing and subsequent mating with the vehicles. Preparations for construction of the S4 test stand at Sycamore Canyon have been completed, and construction will begin in January 1960. In mid-1960, we will enter the captive flight readiness testing program in preparation for the first flight of the Centaur space vehicle, scheduled for June 1961.